All right, we are here. So this is our first Zoom session, and I just want to mention a couple of things. For the time being, we should all be muted to avoid any background noise. Whoops. Oh, that's not what I wanted to do. Yeah, just in case, like the dog starts barking or something. And then if you want to ask a question, you can just turn the microphone back on, and then you can just ask, or else you can send it through chat. So let me just get it. The material is open. So actually what we're doing today is we're looking at the first part of chapter 15, which is our introduction to simple regression analysis. Now, if you look at the slides, they're actually broken up into three parts. This is 15A, and we'll probably get through most of this today. This early part is essentially a lot of definitions, a lot of background material, just to show you what's coming up. As terrifying as it looks, though, just be aware that, as is so often the case, the scariest stuff that we learn can be handled with the old calculator, okay? So that, a lot of the tedious calculations will be done here. But we do have to make sure we understand what we're doing. And so the material today will be pretty intense. But next week, when we come back, we'll go over it again and we'll review it one more time and make sure we all understand what we've seen. And, keep in mind, this is also the only chapter that we'll need for the final exam. So what still needs to be done is we finish this chapter, we do the problem set, we do the sample final, and we're all set for the course. Yes, that's right. So anyway, this material is a little bit different, but yet it still contains a lot of familiar elements. For example, we will be doing hypothesis testing, rather, and other things that we've seen before, but we're going to tie together in an important new way. Now, at some point when we're done with the calculator, I'm also going to show you how this is done in Excel, because it's a skill that you should have for your other courses in business. Okay, at some point it'll come in handy. Let's put it that way. And also, what we're doing here is very useful for research. If you have to do a project in Gabelli, let's say, where you take real world data and analyze it, most likely there will be some regression analysis involved. I don't know if they require you to do anything like that, have a senior thesis or project or anything, but even if not, within your courses, like finance, for example, you may find this to be very important. So anyway, in the meantime, what are we doing here? Well, in a nutshell, with regression analysis, what we're trying to do is estimate the numerical relationship between two or more variables. That's all we're doing. And so, for example, imagine yourself working in a marketing firm, and the corporation wants to know, a corporation wants to know how much their spending on advertising is contributing to their revenues. In other words, they'd like to know how much each dollar worth of advertising is bringing back in revenues. How would you do something like that? Well, you're going to gather up data, and you're going to estimate a numerical relationship between the two, and you're going to find out pretty quickly if the advertising is paying for itself or not. So once that's done, you get more benefits from this, because now all of a sudden you can use your results to actually carry out forecasts. For example, if the same company says, listen, we now know that every extra dollar worth of advertising adds X dollars towards sales revenues. What if next year our advertising budget is $100 million? How much do we expect that to add to our sales? We can ask questions like that with regression analysis, because we have a model in place that explains that relationship. Now, as it turns out, there's two basic types of regression analysis. Sadly enough, we only have time to do the first one. Well, what are you going to do? You can't do everything, right? So we'll do simple regression here, but you should also be familiar with the concept of multiple regression. And what really separates the two is how many independent variables are there. So simple regression will be something that you probably, you'd be more comfortable with this, because all you're essentially doing is estimating the equation of a straight line. Because there's going to be one dependent variable, which is y, and one independent variable, which is x. Well, we've seen this before a few times, so this will be nothing surprising. What's different is that we're taking real world data and estimating the slope and the intercept of this straight line that we're estimating. Now, of course, here's an example you've seen algebraically before. This is a classical example of a straight line. The general formula is y equals mx plus b, as you know, where m is the slope and b is the intercept. So for the example I've chosen here, I've chosen y equals 3 plus 4x. And so 3 is the intercept, which, as you know, is simply the point where the line crosses the vertical axis. That's actually the point 0, 3. Or think of it this way, what is the value of y when x equals 0? Okay, now the intercept is 3, but the slope is what we're really interested in, at least in regression analysis. The slope here is 4, which tells me that every time x increases by 1, y increases by 4, and vice versa. Okay, if y goes down by 1, then the x goes down. If x goes down by 1, y goes down by 4. Okay, so there's nothing new here. So with linear regression analysis, we're making an assumption here. We're assuming that whatever variables we're analyzing have a linear relationship between them. Now, of course, we can't possibly know if that's true or not without having the entire population of data. But what we can do instead is get a sense of whether or not this is true by creating this new kind of graph called a scatter plot. Now, you've probably seen these before. What you're basically doing here is you're taking data from two variables, like sales and advertising, and here, each of these points represents a single observation from our sample data. So, for example, this one point here might be the sales and advertising in the year 2020, and these others would represent data from other years. And so by looking at them, it should be pretty clear that the relationship here, while it's not perfectly linear, is awfully close enough that we can go ahead and use our regression analysis techniques. By the way, that line that I've drawn through the points is an attempt to capture as best as possible that relationship. And we call that a trend line. And the equation of that trend line is of interest to us because it tells us what kind of relationship there is and how one variable affects the other. So we can draw two conclusions from this graph. Number one, the data in our study are at least approximately linearly related to each other. And number two, the relationship is either positive or direct, meaning that x and y either rise or fall at the same time. Now, at the same time, though, there's something interesting going on here. If you notice, those points are not all right on the line, are they? In other words, this is what you'd expect to see with real-world data. The relationship between the two is not going to be perfect. So we have what's called sometimes a probabilistic relationship, which means there's going to be some deviations from one point to the next. So keep that in mind as we go along. There's always going to be discrepancies. Anyway, so back to regression analysis. With simple regression, actually with any regression, there's only going to be one dependent variable. That's all we can have. We can never have more than one dependent variable. What's different is that here there's only a single independent variable, which is our x. Okay, so let's say that we've decided that our sales do in fact depend on advertising. We can analyze this relationship with simple regression analysis because we can think of the advertising as the x and the sales are the y. Because we're saying y is a function of x, sales are a function of advertising. So as long as the relationship is approximately linear, we can use regression analysis to get some reasonably accurate results. On the other hand, what if we've decided that, you know what, our sales are driven by more variables than just advertising? What about our prices? Well, that's probably the case too. So in this case, we're claiming that sales are a function of both advertising and prices. But now we've got two independent variables. So in order to estimate this relationship, we need to resort to multiple regression analysis. Now, the sad news here is that the calculators don't have the ability to do this. For this, we need to go up to at least Excel. And then in addition to that, we may even want to use a formal statistical package. And there's quite a few of them out there to choose from, depending on what you're doing. Usually each discipline has its own favorite statistical packages because every discipline usually leans on different statistical techniques. So, but you may not need to do that at any time soon, but you may use Excel. Excel can do any type of analysis we need. Excel is an amazing tool, but even then it has limits. So this is the case we'll not be considering. And by the way, I just want to mention one other interesting thing. You notice how I call this a probabilistic relationship because the points are scattered around the line. What would be the opposite of this? Well, imagine I'm looking at the temperature in Fahrenheit versus the temperature in Celsius. Well, this is a straight line too, isn't it? Sure it is. F equals 32 plus 9/5 C, which you recall from whatever grade you were in. What's different here is that the points can't be off the line. This is a perfect linear relationship. By definition, the points have to be on this line. And so we call this a deterministic relationship. This is what we'd ideally like to see, but in the real world, we only have probabilistic relationships where there's discrepancies. Here, we don't have that, do we? We do not. I mean, imagine if I said to you, well, if the temperature in Celsius is 20, the Fahrenheit temperature might be, between, That's right. Yes, that's a good question. I'm glad you mentioned that. I'm writing all this stuff. I've been doing this all day with all my other classes. Every time I come up with an idea, I'm adding good things to these slides. When we're done, in addition to posting the videos, the recording of this, I will be posting these handwritten notes as well. Okay. In fact, I changed the title slightly. It's now 15A with notes 11, 21, 23. So when you see it in Blackboard next to the original one, you'll know why. Okay, so you will have a copy of these. So that way, if you don't quite get everything, if you miss something, or if you don't, want to write it down, you'll have a copy of this anyway. Okay. Here's another one I thought would be interesting. What if we're doing medical research between heights and weights? Well, the first thing we always ask ourselves is which one is the dependent and which is the independent variable. So logically, our weight should depend on our height, not the other way around. So therefore, weight becomes the y variable, height becomes the independent variable. Write this out more formally as y is a function of x, weight is a function of height. So what we're going to do, if we want to run a regression on this data, we first do a scatter plot and say, well, listen, is this relationship linear? And now, of course, I don't know if it is or it isn't. I made this up, but if this graph does describe heights and weights, then we can conclude that the relationship is linear and it's also positive, which of course makes perfect sense. Obviously, on average, taller people are heavier than shorter people. Not always. That's why there's scattering among these points. We know perfectly well that some tall people do not weigh a whole lot because they're very skinny. And the same thing can be true for some relatively short people. They might also be very muscular and therefore they're very heavy. So that's why you're not going to see all the points right on the line because other factors get involved in determining your weight. It's not just your height. So anyway, oh, here's a good one. Yes, everybody's going to love this because it involves stocks. Now, here, I just want to, just in case you've never heard of this before, the Standard & Poor's 500 is a stock market index. It is constructed from the 500 largest US stocks, and it's a number that everybody on Wall Street pays close attention to because it reflects very closely the state of the economy. And in fact, any website you've ever looked at that's meant for investors is going to show it to you. For example, CNBC. Okay, now, oh, all those reds are looking terrible. Look at that. Today, the S&P 500 is down 0.9. For God's sake. You know what? Often just before a holiday, the traders are not particularly busy. They're not overly active, let's say, and you tend to get the markets floating around. But this is the S&P 500. Look at that thing. And if you're really interested, you can go to Wikipedia and see a list of the stocks that are included in it. Oh, it's all the big names, that's for sure. That's good, positive information we have here. So if you're thinking about buying stocks, you need to be looking at websites like this one. But anyway, what we'd like to know is how does the S&P 500 affect the returns to Apple stock? Now, obviously, Apple stock is a very successful company, but it's also affected by the state of the economy. So what we'd like to know is if there's an actual connection between returns of the S&P 500 and Apple stock. Of course there is, but we want to know how strong that relationship is. So we gather up our data, just like we did before. We create a scatter plot. And if you notice this time, returns can be negative. So we actually have points in not just the first quadrant, but the others as well. You see that? So yes, again, you can see just from this graph that there is a strong connection there. And also, of course, as the S&P goes up, so does Apple stock and vice versa. The regression analysis will tell us exactly how strong that relationship is. All right. Multiple regression, another example of that. Let's say you're an economist now, and you're analyzing the relationship between the yields on treasury bills and both the growth rate of the money supply and the growth rate of real GDP. Well, clearly, that is not simple regression. There's two independent variables. X1 we'll call the growth of the money supply. X2 is the growth rate of the real GDP. And so therefore, we have a case for multiple regression. All right. So now with all that being said, let's go back and revisit the concept of the linear relationship. Everybody knows the formula or the equation of a straight line. It's something you just don't forget. Y equals mx plus b. M is the slope. B is the vertical intercept. Although there's other ways of expressing this, but this is the most common one. And you might recall that B is, like I said before, simply the point where the line crosses the vertical axis. M is formally defined as delta Y over delta X, which means the change in Y over the change in X. Although you might have been told in high school that it's called the rise over the run. That's just a way of remembering visually what the slope looks like. So really what this is telling us is a sensitivity of Y to changes in X. That's what we need to know with regression analysis. The intercept is usually not terribly useful. Oh, okay. All right, now in Excel, I created some scatter plots. This one appeared, these are two variables that are almost perfectly linearly related to each other. So I don't think we'll have any trouble using simple regression analysis for this case, but let's look at another case. What do you think about this one? Are they linearly related? No, I don't think so. So, in fact, I'll tell you how you know, because the slope is changing. The slope of a straight line never changes. The slope of this one as we get x goes up, the slope is getting steeper. So this is sometimes called an exponential trend. And in fact, if you were to leave money in the bank, let's say, and never touch it, this would describe the balance in your bank account over the years, because in the early years it grows fairly slowly, and then as the interest starts to pile up, it grows much more quickly. And so that is what this would represent. If I wanted to analyze this with linear regression, I would end up with a mess because my straight line wouldn't even come close to explaining what's happening here. So that would tell me, don't use linear regression. Try something else. Okay. All right. Now we're getting close to some deep waters here. We've been wading into the pool for a while now. We're getting ready to dive into the deep end. Just a quick reminder from way back in Stats 1, you might recall that we mentioned that we almost never have access to an entire population of data. We're normally using samples to estimate properties of a population. The classic example being that X bar is used to estimate the population mean mu. So the same thing is happening here. We're going to create a regression line, which is actually a sample regression line based on the assumption that there exists what we're going to call a population regression line that explains the relationship between two variables for the entire population. Naturally enough, the notation is different in both cases. So we're going to start by introducing the population regression line, and then we're going to analyze it, and then we're going to look at the corresponding sample regression line. All right. Now, be prepared for some surprises. All right. Now, maybe this is not the ideal day to be doing such a complex topic. Who knows? What else are we going to do today, right? So the weather is supposed to get really awful later on. So I'm glad that we came up. Well, it wasn't my idea, but I like it, of having this Zoom session. It's kind of fun, and you saved a lot of time driving, right? So anyway, here we go. Be prepared. So this is the equation of the population regression line. Well, what do we notice? First of all, we have all Greek letters because it is, in fact, a population measure. We have the Greek letter beta. That fancy B is beta. And rather than having a separate letter for the intercept and the slope, the more common method is to use beta 0 for the intercept and beta 1 for the slope. But now, all of a sudden, what is that at the end there? Epsilon, the Greek letter epsilon, that is meant to be what we call an error term. And one more thing, if you notice, the variables are indexed. We need to keep track of each one individually. Okay, so for every ordered pair in our our population, we need to keep track of which one is which with our index. And the reason for that is because the error term is unique to each sample. I keep saying that, our population points. Now that looks pretty scary, doesn't it? I mean, it certainly looks like a straight line, except for that error term in there. That's unique. Okay. Here's a nice little graph for us. It's a little crowded, but you can see what's going on. Here's 0.1 over here. That point refers to what we're going to call X1, Y1, the first observation in our population. And if you notice, it's above the regression line. Now that means the regression line goofed. It underestimated the value of Y for X1. In other words, it said, give me X1 and I'll tell you the appropriate value for Y1. But the number it gave me is too much. It's too high. The vertical distance between the actual value of y and the estimated value of y is what we mean by our error term. And we're going to call it epsilon 1 because it corresponds to the point x1, y1. So the indexes are there to keep track of which is which. Now, that error term is positive because, remember, it said actual minus estimated. If we underestimated the value of y, that means we have a positive error. On the other hand, look at epsilon 2. For that one, the true point, the true value of y is very low here. It's below the line, which indicates a negative error term. Ooh. Now, this is a consequence of the fact that we're using real-world data, and we don't expect the points to be directly on the line. We'd like them to be as close as possible, but it's not realistic to expect them all to be on that line, like with the Celsius and Fahrenheit case. Well, is that a problem? Well, it is and it isn't. It's not a problem as long as the errors average out to 0, which indicates that on average, these estimates are correct. Okay, if you notice, sometimes the errors are positive, sometimes they're negative. The way I've drawn it, it's impossible to be sure, but on average, we expect them to be 0. All right. Now, by the way, just as a quick aside, why do we have errors in our data? What's going on here? What's the problem? Why can't we get it just right? Well, there's a lot of possibilities here. Well, for one thing, it may just be that y and x rather, is not the only variable that affects y. For example, the sales example, sales and advertising, it may just be that our sales depend on other variables besides just advertising. And if that's true, we're missing all that information. And that's why we have those errors up there, because that reflects the missing variables. Like, what if, for example, our sales depend on the state of the economy? Well, we don't have that in our model. And so that's why the numbers float around like that. Number two, there may be just plain errors in the data, okay, meaning that whoever gathered the data has mistakes in there. And number three, what if the assumption of a linear relationship is not correct? Now, this graph up here, I tried to show this. What's happening up here is that when x reaches a certain level, cells do not respond as much to advertising. Because people get tired of seeing those ads on TV. We don't want to saturate the market with our ads. So at a certain point, the effectiveness starts to wear off a bit. And so because of that, so the curve flattens out. And that means the relationship changed between X and Y. It's not linear. And that's going to cause us to have errors in our data. Does that make sense? All right. Now I've got another graph full of another diagram. I've been drawing diagrams all day, and it's been fun. But after a while, this document will be mostly handwritten notes. So like this one refers to the weights and the heights. So here's 0.4 over here. And it means that you have the ordered pair x4, y4. Notice this point is above the line, which means we have a positive error. Epsilon 4 is positive. And then up here in the upper right-hand corner, we have error 3. That's 0.3, x3, y3. And this one is negative. So this is very similar to the one we had before. Now, again, the errors are not an issue as long as they do average out to 0. All right, we had to pull the positive errors and subtract the negatives. We're going to wind up with 0. Now, I came up with this analogy this morning and I added it to the notes. Suppose you have a scale at home and it's not perfect. Sometimes it overstates your weight and sometimes it understates your weight. It's a mechanical device. It's not perfect. As long as these errors offset each other, meaning that sometimes it's a little too high, sometimes it's a little too low, but on average it's correct. And you can use the scale knowing that it is reasonably accurate. As opposed to, let's say the scale is always too high or too low, then you can't use it anymore. You have to adjust it because otherwise your results are not very helpful. Like you might say, listen, what's going on here? How come it shows me at 250? I can't be that heavy. So here what I've done is I've shown you some regression lines where exactly that is happening. In the bottom left-hand corner, this is fine. The error terms appear to be essentially evenly matched. They're averaging out to 0. What about the one in the upper left-hand corner? What's happening there? The points are all below the line. That means the error terms altogether are negative. The one in the upper right-hand corner is the opposite problem. So that means if either of those two is the case, the first two, that means we have to do something. We have to like not run the regression or change the variables or do something different. All right. Now, you'll be really surprised to see this. The regression line itself, with the regression line, each point on that line is actually the center of a normal distribution. Wow. So look at this thing. Every one of those points that you see there is the result of calculating a probability distribution. The center is what goes on the line. And they're all normal. So the error terms themselves could be thought of as random variables with their own probability distribution, which is normal. They also have moments. Wow. This is getting very intense. So when you see that the actual value of y is up here somewhere, and this is our estimated value down here, that means we have an error. But the errors are normally distributed. Okay, that's what we're seeing here. And so each of these normal curves has a mean of 0. We don't know what the standard deviation is without further information, but whatever it is, it's the same for every one of those error terms. If it weren't, the curves would be spread out differently. Whoa. So, by the way, I just want to show another graph that I put together where you can see what it would look like if the standard deviations were not the same. So the one on the left, everything's fine. Okay. They all have the same mean of 0, which is fine, but they also have the same standard deviation. The one on the right, whoops, they're not all the same, are they? That's a problem. Wow. Okay, you see what I mean? They're not all spread out equally. So the one on the right, they have different standard deviations, and that is a problem that we have to contend with. All right, and we'll see more about that later on. And also, what I wanted you to see here too is that if every situation is different. If you're comparing two variables and you end up with this regression line here on the left, if you notice the points are really, really close to each other, that means that the standard deviations of those error terms are very small. We can have a lot of confidence in our results. The one on the right, it's the other way around. The standard deviations are enormous. So the points are scattered all over the place. And that's how we would know that we cannot have a lot of confidence in our results. Okay, and one more detail here. We're going to assume that the error terms are independent of each other, which effectively means there's no pattern to them. Okay, now watch this. In the graph on the left, the points are randomly scattered around the regression line. There's no pattern to the errors. Some of them are large, some are small, some are positive, some are negative. But look at the right. What's going on over there? Ooh. In the right here, we have only positive error terms, one after another, and then all of a sudden they're all negative. That means there's a pattern to the error terms, and that means they're not independent. And that in turn means our assumptions are being violated. Something needs to be done to correct for this. Wow, look at that. A pattern, we don't want that. We want them to be random. All right. Does everyone see that? That's what it means to be independent or not independent. Okay, now here's an issue we haven't addressed. What equation should we use to create this regression line? Well, there's different options that we have, but the one we're most likely to use, and we'll only use that in this class, is a technique called ordinary least squares. This is the one that's most commonly used. It's the simplest one, and it works very well unless we have major violations of the assumption of regression analysis. Then we have to try something different. All right, so the majority of the time, this is what we're using. In this class, this is the only technique we'll be using. And that's what's built into your calculator and Excel, the ordinary least squares technique. Okay, so what is this all about? Well, you'll see in a second what it will be done, what will be used, it will be used to come up with formulas for calculating or estimating our sample regression line. So for the first time now, I'm going to introduce you to the sample regression line. We've seen the population line for a while. Let's look at the corresponding sample regression line. All right, here we go. So the one on top, we know already, that's our population regression line. The one below it is the sample regression line. So how are they different? Well, as we know, we always use the Roman letters for sample measures. So the betas have been replaced by B's. The Y, on the other hand, was already a Roman letter. So to make it into an estimate, we have the technique, the notation is we put a caret directly above it. And theoretically, we should call it Y caret, but for some reason, people tend to call it Y hat. All right, Y hat, I know. Looks like a little party hat, doesn't it? Yes, it does. But also, what happened to the error term? Well, because it's averaging out to 0, we don't need to bother estimating it because our best estimate of it is 0. Okay, So that is the final result. That's what our calculators will be estimating for us. Ah, I see. So there's two lines. The one that we'll never observe is the population regression line. The one that we'll get in our calculator is the sample regression line. So one more thing, though, we do have to take into account here. The epsilon, though, was what we mean by an error term, but it turns out there is an equivalent sample version, EI, which is called a residual. And that is calculated in the same way. In other words, it is the difference between the actual value of Y and the estimated Y. So think of it as the sample version of an error term. And the properties of the error terms are assumed to be shared by the residuals. In other words, we expect the residuals to average out to 0 and be independent of each other. Well, so here's a quick little graph, and you get, it's the same idea. This point 1 here, which is taken from sample data now, has a positive residual because Y is greater than the estimated Y. Down here, this could be thought of as X2, Y2. It has a negative residual because the actual Y is less than the estimated Y. And to tie all this together, the OLS technique tells us that the line that we will estimate is obtained by calculating the minimum sum of squared residuals. Okay, in other words, when you see it working, this is what it's actually doing behind the scenes. It is finding the unique combination of slope and intercept where this number is as small as possible. All right. Now, I'm going to show you an example here with two lines that we could choose from, and we're going to figure out which one we should pick. Let's say you were confronted with these two choices. Which one would you pick, line A or line B? Well, line A at least goes to the points. B is a terrible choice. Look at that. It's almost below every one of those points. That's because the sum of the squared residuals is larger. We picked A because its sum of squared residuals is smaller. And that's all there is to it. Oh my God. Now, that's all we need for now. I think everyone's had enough of this. And plus, it's just before Thanksgiving. And maybe you're not thinking completely about school right now, and you're looking forward to your vacation, which is good. But next week, we'll just go through this again one more time and make sure we all get it. And then we can actually start doing some examples. What we're going to do is put the X's and Y's into our lists and let the calculator run the actual regression analysis. We're going to focus our attention on analyzing it, okay, as opposed to calculating it. So that will help a lot. So anyway, now we have a feel for where we're going with this stuff. But remember, the calculator will do most of the gruesome work for us and let us figure out the analysis. So that being said, I think we may as well go off and head off to our Thanksgiving vacation now. Unless you have another class. Oh my God. Now, I don't know how they could possibly have presentations online. Well, maybe they could. But that nobody is. Yes. Okay. So yes, we're definitely done. So I'll see you all next time.
Happy Thanksgiving.
Everyone. Happy Thanksgiving.
Next time.
Thanks, guys.
All
Thanks,
right, bye.
Professor. Have a good Thanksgiving.
You too.
All right. Thank you.
Okay, bye.
Bye.